All right, we're now going to be combining some like terms in order to write our complex number answers in A plus BI form. So again, let's do a quick review that complex numbers have two parts. They have this part in the front, the constant, which is the real part, the real number. And then at the back, they have the BI or imaginary part. And so standard form of a complex number is written with the real part in the front and the imaginary part at the back. So when we write our answers, we're going to write it in A plus BI form. So in combining these like terms here on the first one, part 2A, we're going to rewrite this with no parentheses. Oops. We have a 1. We have a minus 8i. We have a plus 4. And we have a plus 2i. And then we're just combining like terms of the real numbers or the constants, 1 and 4, and then the imaginary parts, the negative 8i and the 2i at the back. So for our real part, 1 plus 4, we're going to get 5. And for the imaginary part at the back, we get negative 8 plus 2 is negative 6i. And there's our final result in A plus BI format. Okay, on the next one, we've got a minus in the middle. And so what that means is when I'm rewriting this without parentheses, is that this negative is distributing. It's going to change it and turn it into a negative 9. And the negative times I is going to become a negative I. Then we're going to combine both the real and the imaginary parts. Here's the real parts. Here's the imaginary parts. Let's put those together. 2 minus 9 makes negative 7. And negative 4 minus 1 is a total of negative 5 i's. There's my A plus BI format. We're done. Next one also has a negative in the middle, so I'm going to go ahead and rewrite it without parentheses, but remember to change these signs when I distribute this negative. Negative times negative 8 makes positive 8. Negative times negative 5i makes positive 5i. I'm going to combine both the real and the imaginary parts. 10 plus 8 makes 18. Negative 1i plus 5i. There's my complex number with both real and imaginary parts in the A plus BI format. All right, on this next row, we're multiplying. We're getting the product of complex numbers, and we need an important rule. I'm going to put it off to the side here. Remember that by definition, I squared equals negative 1. And so when we're getting to the end of this simplification process, we're going to need this rule. You can use both the FOIL or the box method on this. We experimented with both. I'm going to demonstrate FOIL. 3 times 7 is the first times the first term. 3 times 2i, sorry, that's a negative 2i, is going to be the outer times the outer. 5i times 7 is going to be our inner. And last is 5i times negative 2i. Now this row of work that I just showed, most people do this part in their head. I just want you to see all the groupings of what I'm doing. First times first, outer times outer, inner times inner, last times last. And so now we go simplify this out. 3 times 7 is 21, minus 6i, plus 35i, minus 10i squared. In this next step, I'm going to do two things. I'm going to combine these like terms in the middle, and back here, negative 10 times I squared, can't that be simplified as negative 10 times negative 1 is just positive 10. So we get 21 plus 29i, so 35 minus 6 is 29, plus 10. Final answer, this 21 and 10, we're going to combine those like terms. to make 31 plus 29i. Now we're done. There's my a plus bi final result, final expression, final simplification. Okay, try pausing it and experiment with the next one and then see how you did. Okay, for this one, I'm going to demonstrate the box method so that you can remember back to which method you prefer. It doesn't matter if I write it across the top or across the side. And then I multiply. -9 times 7, that makes -63. 7 times I, positive 7i. Negative times negative is positive 9i, and negative I squared at the back. When I write this all out, I get -63. 7 plus 9 combines to give me 16i in the middle. So these two terms are like terms and can be combined. And then at the back, I get -I squared. Well, by definition, we know that -I squared could be rewritten with I squared as -1. So it's like saying -1, which is a positive 1. And then we combine like terms. -63 plus 1 is -62 plus 16i. Done. There's my complex number with both the real and imaginary parts in a plus bx format. The next one is something squared. So recall that you can stretch these two factors out and then multiply. Do you want to do the box method? Do you want to do the FOIL method? Pause the video, try it. Okay, let's see how you did. There's my complex answer with both the real and imaginary parts in a plus bi format. Okay? All right, again, the final one, I want you to pause this and really dig deep. Can you solve by square roots? Can you solve complete the square? Can you solve using the formula? Pause it, try it. Okay, let's see how you did. Oops. There. All right, so break down that 60. 6 and 10, 15 and 4. Six times 10 breaks down even further. All right, what can come out? What stays in? Final answer. I just got my two complex roots, or my two non-real roots. Okay, next one I'm going to do again with complete the square because we have a nice even b. Step 1, make space. Step 2, b work. Add and subtract. Factors. Simplify the back. Here's my vertex form. My vertex would be -6,4, but we want to keep going. We want to solve. Move that constant. Root. both sides. Minus the 6. We're going to get negative 6 plus or minus square root of negative 4. But we know we can keep going on that. The square root of negative 4 would be rewritten as 2i. So if I wrote these out separately, it's negative 6 plus 2i and negative 6 minus 2i. Those are my two complex roots. All right, here we go. Whole enchilada for the formula. If you didn't pause the video and try this, you better do it now. Okay, let's see how you did. Well, that's a big C, huh? $12 times 20 is 240. I got to grab my calculator for this one. Hang on. 12 times 20, 240. And we're going to subtract that 64. We're going to get negative 176. Now I know an I can come out, but I want to break this down and see if anything else can come out. So let's divide 76 by 4. Oh, it works. Sorry, 176. 176 divided by 4. That breaks down into the square root of negative 1. And 176 is 4 times 44. Or 4 times 4 times 11. So a 4 can come out and an I can come out and a root 11 stays in. So this right here is what we substitute in or plug in right there. So we get negative 8 plus or minus 4i root 11 over 6. And in our final step of simplification, 2 divides into everything. So we say negative 4 plus or minus 2i root 11 over 3. There are my two complex roots. How'd you do? If you wanted to split this up, you could have written it as negative 4/3 plus or minus 2i root 11 over 3. Both of those answers would be acceptable. All right, last one, number 5. Erica wants to algebraically find the x-intercepts for this function. Kyle saw her work and said that the steps were correct but not her answers. Identify the conceptual mistakes she made in her answer and explain. So check this out. Step 1, make space. Step 2, add and subtract. Step 3, factors and simplification. And we got 105 minus 25, that is 80. Step 4, move the constant, subtract the 80 to the other side, good. Step 5, square root both sides. Step 6, break down the root 80. So this is going to be a 4 comes out, an I comes out, and a 5 stays in. And then minusing the 5 from both sides. Okay, so do you see how all of the steps make sense, right? Like everything that she did worked as far as her work of getting the roots. But I want to pause for a minute and talk to us about these non-real roots. What makes them non-real is having a negative under the radical. We know that as the discriminant. When we have a negative discriminant, we know that there are no real roots or no x-intercepts, because essentially you have a graph that never touches. So we cannot put these as x-intercepts with a comma 0 because there are no x-intercepts. So we cannot write out these roots with comma zeros. In this case, there are no x-intercepts. Does that make sense? Like all this work was correct, but you can't write out x-intercepts because there aren't any. So that's the conceptual mistake they made at the very end. All the work was beautiful, but what are we actually dealing with here? No real roots, no x-intercepts. How'd you do?